Today's learning goal is to describe the motion of objects in freefall. Describe the motion of objects in freefall. So we're going to consider the situation of an object falling in Earth's gravity. So imagine, for example, a tennis ball. It's dropped from a height. We're going to call this initial position of the tennis ball just before it's dropped. We're going to call that a height h. And then once the tennis ball is released, it's going to start speeding up towards the ground. So at 1 second, it'll move a little bit, and it'll be going kind of a slower speed. After 2 seconds, it will be moving faster. After 3 seconds, it'll be moving faster still. So this tennis ball accelerates as it falls. So I want to go ahead and find the position time graph, the velocity time graph, and the acceleration graph for this situation of the tennis ball falling. So the initial position of the tennis ball at time equals 0 is a height h above the ground. So we're going to say that the initial position of the tennis ball is at h. And then after 1 second, the ball has moved down slightly. And after 2 seconds, it's moved even further down towards the ground. And after 3 seconds, it's over here. And after 4 seconds, it's at the ground. So let's try to draw the velocity time graph. So remember that the velocity time graph is the slope of the position time graph. So we're going to be able to get the velocities for our velocity time graph by looking at the slope at different times here in the position time graph. So initially, the tennis ball is not moving. Right when it's released, it's going to start speeding up from a velocity of 0. So initially, our velocity is 0. And notice here the slope of our position time graph, it looks very flat. So if you were to imagine a little line tangent to this graph at time equals 0, the slope of the graph would be 0. Then at time equals 1, we can see now the slope is slightly negative. So let's go ahead and start plotting velocity here. It's going to have a negative value because it's a negative slope of the position time graph. And then as time passes, this negative slope becomes steeper and steeper, meaning that the velocity of the tennis ball is increasing in this negative direction, right? So we can see that the slope of the position time graph is getting steeper and steeper and steeper. So the velocity is increasing in the negative direction. I'm going to try my best to graph this properly. So we should get a straight line. My graph came out a little wonky, but that's okay. So our velocity time graph should look like a line with a negative slope because the velocity is increasing in the negative direction as time goes on, and the ball speeds up faster and faster and faster, falling under gravity. Okay, so next we can find the slope of the velocity time graph to find the acceleration. And notice the slope of the velocity time graph, it's the slope of a line, so the slope is constant and it's a negative slope. You can see here our velocity has a negative slope, and the slope is not changing. So our acceleration is going to be a constant negative acceleration. Okay, and for the Earth in particular, at the surface of the Earth, the acceleration is negative 9.8 meters per second squared. So this is a very important value for us in physics. We call this the acceleration due to gravity at the Earth's surface. It has a value of negative 9.8 meters per second squared in the y direction. By the way, so let's define this convention. We say that the positive y direction points up away from the ground. So we say the down direction towards the center of the Earth is the negative y direction. So our object is accelerating in the negative y direction because that's the direction that gravity points. It's wanting to pull objects down towards the surface of the Earth. And notice right here we're ignoring air resistance. So this is true in situations where we can say, okay, the air resistance is not going to play a big role, so we should not use this value for the acceleration due to Earth's due to gravity at the Earth's surface for an object that's, say, moving extremely fast. So imagine something being dropped out of an airplane where there's a lot of air resistance as the object falls and gets to higher and higher speeds until it reaches terminal velocity, right? It's no longer going to be accelerating at this rate. Or, for example, a feather being dropped and slowly coming down and settling onto the surface of the Earth. That feather is not going to be accelerating. We're going to consider only situations where ignoring air resistance is a reasonable thing to do. Okay, the other important thing here to notice is that this value, 9.8 meters per second squared, we can write that as little g. So this is a constant little g, and it represents the magnitude of the acceleration due to Earth's gravity at the surface of the Earth. Okay, so let's go ahead and try a problem. So we have a problem here that says a hammer falls from rest for 4.1 seconds. So after being released, the hammer falls for 4.1 seconds. What is the velocity of the hammer just before it hits the ground? Okay, so there's some implied information here. The first one is that this hammer is falling on the Earth. So it didn't specify that it's falling on the Earth, but that's what we assume because we live on the Earth. So if it's falling on another planet, then the acceleration might be different than the acceleration of gravity here on Earth. But if the problem doesn't specify, then we're going to assume that it's happening here on Earth. So the acceleration is going to be negative 9.8 meters per second squared. Then it's saying that the hammer falls from rest, meaning that it was initially not moving. So our initial velocity is 0 meters per second. Next, we want to know what is the final velocity of the hammer. So v final is something that we're going to be looking for. And 4.1 seconds is our time interval. So delta t is 4.1 seconds. The hammer is falling for 4.1 seconds. Okay, so we're going to use our acceleration equation. Acceleration is a change in velocity over a change in time. Change in velocity means final velocity minus initial velocity. So let's go ahead and start substituting in values. Acceleration is negative 9.8. The final velocity we don't know, so we're just going to leave as final velocity. The initial velocity is 0, and the time interval is 4 seconds. So v final minus 0 is just v final, and we should try to solve for v final, so let's rewrite negative 9.8 equals v final over 4. So in order to try to get v final by itself, we need to move 4 over to the other side. We're going to do this by multiplying because right now it's dividing v final. So to undo that division, we're going to multiply 4 on both sides. So our 4's cancel, and we're left with v final is equal to 4 times 9.8, sorry, negative 9.8, which is going to be equal to negative 39.2. The units for velocity are meters per second, and the direction of the velocity is in the y direction. Okay, so that's it. That's our final answer. So now I'm going to give you one to try. This one says a rock falls off a cliff. If the rock is moving at 30 meters per second by the time that it reaches the ground, how long was it in the air? So we want to know for how much time did the rock spend falling. So go ahead and pause the video, try this one on your own. Okay, hopefully you tried it so that you can get some practice working these problems out yourself. But here's the solution so you can check your work. So it's saying a rock falls off a cliff. It doesn't say that it's like a cliff on another planet, so the acceleration is going to be the acceleration due to gravity on Earth, which is negative 9.8 meters per second squared. The rock is moving at 30 meters per second by the time that it reaches the ground, so our final velocity is going to be negative 30 meters per second because the rock is moving downward. It's falling. The initial velocity is 0, so it didn't say that the rock was thrown. It's just falling off a cliff. So the initial speed is going to be 0 meters per second. And we want to know how long was it in the air, so our question mark is the time. Okay, so let's write down the equation. Acceleration equals change in velocity over the change in the time. We're going to substitute in values. So a is the acceleration, negative 9.8. The final velocity is negative 30 meters per second. The initial velocity is 0 meters per second, so we'll subtract the initial velocity. Right, change in velocity is final velocity minus initial velocity. And then we're looking for time. So now we have an algebra problem to solve here. The variable that we're trying to solve for is in the denominator. So our first step should be to try to get this variable out of the denominator. So we're going to multiply both sides of the equation by delta t to move it out of the denominator. So delta t cancels on this side, and we've got negative 9.8 times delta t equals negative 30. And now, remember, we're still trying to solve for delta t, so right now it's being multiplied by negative 9.8, so we need to undo that by dividing both sides of the equation by negative 9.8. And negative 9.8 then cancels on this side, and we're left with delta t equals negative 30 divided by negative 9.8. Which is 3.1 seconds. And this is our answer. Great job, everybody. Nice work.